in this kind of framework. And this can then be used for analysis of complex systems and also for identifying what needs to be repaired at which point in time, in which way. We tried to use this concept for a cost-effective and customer-oriented regeneration of jet engines. So what we did is basically, we looked at what happens if a jet engine comes to the factory for maintenance and repair. And in the first place, we just looked at the axial compressor. Now you can imagine this machinery is very complex, and an analysis, a physics-based analysis of the jet engine or even of the compressor is almost kind of hopeless. But we tried to model the key dependencies in the engine and in particular in the compressor with a functionality-based model. So the question is basically, if the jet engine comes to the factory, what part to look at first for the repair and how to repair which part so that we make a cheap repair and we meet the customer requirements with the result in the best possible way. So what we did basically is we used a simplified model for a physics-based analysis of the compressor combined with the data analysis and expert knowledge. All these three components basically describe the key influence we are interested in. In our case, this was the dependency between the blade roughness, which reduces basically the airflow through the turbine if we have a very rough surface, and the performance of the compressor. So we investigate the dependency of the compressor performance based on the blade roughness. Based on the initial analysis combined with data and expert knowledge, we identified a very simplified functionality-based systems model which describes basically the performance of our compressor independent on the surface roughness of the blades. So we then formulate basically failure of the system as this performance of the system is getting below an acceptable level. So this is basically a meta model for this dependency. Once we have found this meta model, we can then identify the survival function, which describes basically the degradation of the performance over time when the roughness on the plates develops over time when the aircraft is flying. Now this depends on the conditions where the aircraft is flying and so forth. In addition, we can then say, okay, based on where the engine was flying and what kind of measurements we do when the engine is delivered in the factory, we can then identify at which point in time which of the parts in the engine is the most critical part at that point in time, and to look at this for the repair and maintenance first. So in this way we can control the regeneration of the engine, we identify the most critical component, and we get guidance for diagnosis and repair. And we see that the fourth rotor stage, which is number 3 here, is the most important one. So this is the purple line. But the yellow one, which is type 2, is the second most important. So we have an order of how we look at the parts in the engine and make decisions when to repair which part, and then also to which degree. To which degree means we need to improve the smoothness of the surface on the turbine plates, and then we see how the survival function looks like if that meets the customer requirements. Now this is a complicated decision-making process because we have different options for this repair and maintenance in order to reach a certain level of quality. So the key questions we have to answer in this regard is: which target quality level of the regeneration is optimal? How much time should we spend on the regeneration? How much should we invest on which part to repair it? And which technology and process should we use to repair our engine? So these are the key questions we have to answer on site. In order to answer these questions, we do not only look at the state of the engine when it is getting delivered, we also look at the time we need for the repair, the money we need for the repair, and the quality basically which comes out, how this satisfies the customer requirements. Customer requirements is basically where should the aircraft fly, what kind of quality they would like to have, and also how many takeoffs, how many landings and so on they expect for this aircraft in the next few years' time, and so on. So we need a concept which covers basically the life cycle, at least for the next period, until the aircraft or engine comes back for repair. So this sounds, in civil engineering terms, like a resilience-based life cycle management problem. So we basically borrow the concept of resilience for this kind of problem. So we have the reliability of the system. So basically performance is okay. Then the performance goes down over some time until we reach a level where we need to maintain our aircraft turbine. This is then the recovery time, and then it's getting up again with the quality improvement of the surfaces, of the plates, until we reach the desired level given by the customer specifications. So this concept is based on resilience, so we need a mathematical expression for it, and here we borrow the resilience matrix by Ouyang and Leonardo from Rice. So we express basically resilience as this ratio. If we go back to the last slide, this is basically the area under this curve with respect